Hi, let's do some math. So here we go. We are on lesson 1.4 or something. I don't know. Transformations of absolute values and quadratic functions. So the last lesson, we talked about how the different parameters can change our functions. So now we're going to actually put it into practice using some specific functions, including the absolute value and quadratic function. So let's spark your learning. A professional stunt rider performs a jump between two ramps. The jump follows a parabolic path as the force of gravity pulls the rider back down to the earth. The ramp has been placed at a 45-degree angle so it does not factor into determining the range. The two ramps are d meters apart. What is the mathematical question you can ask about this situation? What information would you need to know to answer these questions? So some, kind of math questions that you could ask, like exactly what path, what is the equation, what specific parabolic path do they take, how long is he in the air? We could use that information. The distance between these two, we could use that. All things that would help us to know more about this situation and to help this stunt rider. So then it gives us some of this information. The bicycle leaves the ramp at a speed of 13 meters per second. Gravity pulls down the bicycle with 9.8 meters per second squared. The ramp is 15 meters apart. And let's see, it was a 45-degree angle. So then this just becomes a nice little physics problem that we have to do some math so that we can figure out whether or not this poor guy is going to make it there. Now, obviously, this guy's probably not doing the math in his head right now as he's flying through the air. But this is something that you could do as a stunt rider before you do a jump so that you can kind of sort of make sure that you're going to make it to the other side. We're not going to do that math now. We are going to continue on. We are going to start by analyzing absolute values and quadratic parent functions. As I'm sure you remember what an absolute value is. An absolute value, where'd you go? Come here, absolute value. Is this guy right here. We use the straight brackets to indicate absolute value. And it basically just kind of drops the negative sign. So this, mathematically speaking, is defined, the absolute value function is defined as, if x is positive, then x is greater than or equal to 0. And then if x is negative, so the absolute value is negative x if x is less than 0. So meaning, if this x right here is a negative number, then this function indicates that it is a negative x. So a negative times negative equals a positive. That is a very fancy mathematical way of saying drop the negative sign. That's all absolute value is. And then, let's see here, we're talking about quadratic functions as well. So here is our basic version, ax squared plus bx plus c. And I'm pretty sure that this is supposed to say where a does not equal 0. Because if a equals 0, then we don't have an x squared, and it's not a quadratic function anymore. But the parent function, so the word parent function, we're going to be using that over and over again. That's like the basic starting point of a function, where we didn't change anything, it's just where it starts. So the parent function is just going to be x squared. And again, as I'm sure that you remember, the graphs of these functions look like this. So here's our absolute value. It's basically a line going up both ways because we're dropping the negative sign on our f of x or our y functions. And over here is our parabola. Oh, Mr. Lin, it's so hard to remember all these parent functions. Well, the next time you're in class, take a moment and look left. Yeah, just look left. Maybe that could help you. I don't know. So we're going to look at some of those characteristics about our absolute value and quadratic formulas. So which statement best compares the domains? So remember, is domains x or y? Hopefully you were thinking to yourself x, so we can look at our x values. For what x values can we plug into these and have a value? So the answer is all values. So this one, it's a little bit less apparent, but if you remember x squared, think about what values can I plug in for x and I would actually get a number out for. So you can plug in any value you want. There's no values that are restricted. So the domains for both of them are going to be all real numbers. Or in this case, since they have it written in interval notation, it's going to be negative infinity to infinity. The domains, domains and ranges. Okay, yeah. So domains, all real numbers. Ranges, though, so do you see either of the graphs down here on the negative side? Again, hopefully the answer is no. So the ranges are going to be from 0 on up. So the domains of the two functions are the same, but that's not it. Domains of the two functions are the same, negative infinity to positive infinity. The ranges of the two functions are the same, 0 to positive infinity. Yay. Determine which features are the same for both graphs. So the vertex, if we look at the vertex, 0, 0, 0, 0. So they're going to be the same. Intervals where they are increasing, so where the graph is going up, that's going to be the same. Where it's decreasing, again, that's going to be the same. The end behavior, they are both going to go to positive infinity. And the end behavior as x increases without bound. Yeah, so they're both the same. So notice how there's a lot of similarities. That's kind of why they got grouped together. Yay. Does the symmetry of both of the graphs describe the symmetry of both of the graphs? So if you remember, which I certainly don't, the definition of even is something along the lines of, let's write it. What was it? Net f of negative x equals negative f of x. Is that right? Negative 1 equals f of 1, but negative. Yeah, so we'll go with that. I think that was our definition of even. But they both have a line of symmetry going up through the y-axis, and they are both even. Oops, I pushed the wrong button. Come on. Even. Even. Oh, good. I was hoping I didn't mess that up. As hopefully you have anticipated, we are now going to be transforming our absolute values and quadratic functions. So remember, let's see if I still have it up. Yes. This is our, transformation hinty graphy thing right here. So all of this is still going to hold even when f of x is an absolute value or the quadratic function. So let's see how we do. Describe how to transform the graph of a parent absolute value function, f of x equals x, to obtain the graph of the function, all of this. Then draw the graph of the function. So we're going to pull up our handy dandy little cheat sheet here. And we'll just go, okay, fine. Can I highlight? Nope, of course not. It's like too easy. So we're just going to go left to right again. And we'll label each chunk of this as we get it. So to start off with, we've got this -2 here. So we've got this -2 there. We're going to zoom in a little bit. So our A is going to be equal to -2. So that's what that part's right there. So then inside of the function, we've got two things going on. We've got that 1/4, and then we've got the x plus 1. So inside of the function is 1 over b. So our b is equal to 4, because right here it's 1 over b. And then up here it's 1 over 4, so b is equal to 4. And then we've got x minus h. Here we have x plus 1, so h is going to equal -1. So this sign always changes. Okay, don't forget that. And last but not least, we have this -3 on the outside, so our k is going to be equal to -3. So now we can go through and answer some of their questions. So a equals -2 is so it's outside the function, it's going to go up and down, so it's going to be a vertical stretch by a factor of 2 and a reflection across the x-axis. Bam. B equals 4 is a horizontal stretch by a factor of 4. H equals -1. So again, that's inside the function, going left to right. So that's going to be a horizontal translation left 1 unit. Then what's left? Bam! You got this, right? So it's those same parameters. We're just applying it to an absolute value, right? Yeah, we're doing absolute value. So which transformations occur inside the function f and which occur outside of f? So that's kind of what we've been talking about. The horizontal stretch and horizontal translation all happen inside. And then the vertical stretch and the vertical translation both happen outside. So our vertical is always outside. Our horizontal stuff is inside. Yay. So now we can create a mapping rule for the combined transformations. So remember, applying the transformations to any point x and y will result in this type of formula. So you can derive this part one of two ways. You can either think to yourself and just kind of logic through, like, okay, what's going to happen to all of my x's? Okay, well, when we put an x in, it's going to, x's are horizontal, so, it's going to be multiplied by 4, and then it's going to be moved, then subtracted a 1 from it. Or if you're more of a memorizing type of a person, earlier in our last section, I had to write it down because I don't memorize it very well. We had this little thing that they secretly gave us, bx plus h, ay plus k. So this is always true, and you can always use that to then transform some of your points. And so you'll see that this right here follows that as well. So b is 4x minus h is -1. A is -2, and then plus k is -3. So that's where they got that from. And now we can apply the transformation to any of the points that we had. So let's see here, which parameters impact the x-coordinate? Okay, so we kind of already answered that. So if we had these what am I trying to say? These reference points here on F were the corresponding points on G. So we just plug those things in for X and Y into this formula up here, or into this new formula. So let's go ahead and write that down, because I'll need that. So that's going to be 4x minus 1, negative 2y minus 3. So then when we do negative 1, we shove that in there. It's going to be negative 4 minus 1, so that's going to be a negative 5. And because it's multiple choice, I can kind of cheat. So that's the only one that has negative 5 in the x. 0, 0 is going to be easy. That's going to be negative 1, negative 3. And then probably the only one that's left, so if we shove 1, 1 in there, it's going to be 4 minus 1. That's going to have x equals 3. So these are our new reference points. So we can plot those onto a graph, and then bam, it looks like that. Don't you guys like my drawing? I'm really good. I have an idea. Let's do the exact same thing with a quadratic function. So that's where we're going with this. So let's take our quadratic parent function, which is f of x equals x squared, and let's figure out the transformations from that. So we zoom in, pull out our little cheat sheet. So there it is right here. And away we go. So there is no number here in front. So then what does our a equal? If you said 1, you are correct. If you said 0, you are wrong. Sorry. So our a equals 1. Our b is inside of the function. So here we have a 4 inside of the function, but our b is 1 over b. So in this case, our b is going to be equal to 1/4. Because when we plug that into this equation down here, into this part right here, it will then turn into the 4 that we see there. So I bring that up over and over again because I don't want you to get confused by it. So then we have an x minus 2 on the inside of the function. So then that means that our h is just going to be positive 2. Because remember, we already have a negative here and a negative there. So our h is then positive. Again, trying to make it so you don't get confused with it. And then our k, I always feel like the k is easy. It's just the whatever number is out here. You don't have to do anything strange with it. So using that same chart and these values, let's see what we got. So a is outside the function, so it would be a horizontal vertical stretch or compression. Since it is a 1, there is no vertical stretch. B is inside the equation. It is less than 1, so it's going to be squished a little bit. So that's going to be a horizontal compression by a factor of 1/4. Let's see here. The h is in the inside of the function, so it's a horizontal translation, and it is positive, so it's going to go to the right 2 units. And then k is a vertical translation up 1 units. Yay. There was much rejoicing. Again, they're asking which transformations occur inside the function, outside, and which ones are outside the function. So that's something I've been going over a bunch. I'm not going to go through that part again. So create a mapping rule. Apply these transformations to any point, x and y, on the parent graph, the resulting point. So again, the place that they got this was the, I'll put it in red again, because that's the thing that you need to know. Come on. B of x plus h, a times y plus k. So then when you substitute all of our parameters in there, we then get this thing that they have right here, which I will write out. 1/4 x plus 2 y plus 1. Y is going to be pretty easy. Which parameters impact the x coordinates and which impact the y coordinates? Again, the things on the inside of the function impact the x because they're moving left and right. Things on the outside of the function affect the y because it's moving up and down. And so here we go one more time. So notice we picked the same reference points. Those are pretty solid reference points to pick when we're dealing with quadratic and absolute value functions because they just happen to be in pretty convenient spots. Like this vertex, that's always a good one to start off with. So if we shove 0, 0 into all of that stuff, we get 2, 1. Boop. Easy. Let's see here. The other two are not going to be easy. So if we put -1, 1 into it, so my y value is then going to be 2. They're both 2. So now I got to do even more math in my head. So we got -1 goes in there. So now we have a -1/4 plus 2. So 2 minus 1/4 is like 1 3/4, which is like 7/4. Yeah. I did all that in my head. I'm mildly proud of myself right now. I'm really not good at doing math in my head. Most of you will do basic arithmetic better than me. Just saying. And use the transformed reference points to graph the function. Are we ready? I want you to graph it in your mind. Does it look like that? Good job. But again, notice the way we would graph this is we have 3 points and we kind of know what they respond to. We have our vertex and we have these 2 up here. So then you just connect the points with an arrow and you're good to go. You know it's a parabola, so you know it's going to curve. And you know the vertex, so you should be good to go. Model with absolute value and quadratic functions. So this is kind of their stab at a kind of a real world situation. And of course, engineers, especially structural engineers, are going to use things like these precise formulas all the time. So for example, quadratic formulas, the St. Louis arch is what is called a catenary arch, which can be expressed as a quadratic function. And looks like we've got some towers here that can also use some of the function we're talking about. So this, the one tower design probably uses absolute values, maybe, yes. This one right here, the 2 tower design, ooh, look, a curve. Gee, that's weird. Could that be a parabolic curve? So, engineers working on a bridge projects are considering 2 different designs. One design has a single tower supporting the roadway. The other design uses 2 towers. The engineers need to determine a mathematical model for the cable in each design. The figure shows drawings of cables with the coordinate grids used to identify key points on each cable. So I'm just kind of looking over these. Looks like their height, no, their length is 250. Height over here is 100. Height over here is 70. These are things that, as an engineer, kind of matters. Perspective, so 0, 0 is right here in the bottom left-hand corner, so 0, 0 is going to be right here. Things that I'm just kind of looking at as I look at these pictures before I move on with the questions that they're giving. So the model for the outermost cable of the 1 tower design this one right there, has the form blah, because it's an absolute value, where x is the horizontal distance in feet from the left end of the roadway, and C1 of x is the cable's height in feet above the roadway. The model for the cable of the two-tower design has the form, so same thing, just quadratic formula, where x is the horizontal distance in feet, and the left end, okay, blah, 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 blah. So which 2 points in the figure of the one-tower design could you use to determine h and k in your model? So they gave us the one-tower design has a form that, where this is the outermost. It said that somewhere, right? Yeah, outermost cable. So we need to know h and k. So this is an absolute value. Normally, absolute values start at the origin and go up. So our h and k are, how does that vertex move? Well, it moved to the right. How many units? Boop, 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 boop. And then it moved up how many units? Boop, 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 boop. So our k is going to be equal to, that's the up and down, is going to be equal to 100. And then our h is going to be equal to 125. So which 2 points in the figure of the one-tower design could you use to determine h and k of the model? And then solve for a. So we have h, we have k. Are they just asking which point we use? We'll use that point. Oh, and then we got to find a different point so that we can solve for a. So let's see here. Honestly, I think we can use any point we want. Yeah, so I think we can use any point we want for to find k. I'm sorry, to find a. So I'm gonna say let's use a really easy point like 0, 0. So if we do that, so if we use 0, 0, and I'll switch to red, that means that if we plug everything in, 0 equals a absolute value of x is 0 minus h, which is 125, close absolute value, plus 100. Okay, so we can do that math. So 0 equals a times 125 plus 100. So notice how this was a negative, but I dropped the negative because it's an absolute value. So now we're going to put the 100 on the other side. Equals a 125. Then we're going to divide both sides by 125. Then we're going to have a equals, it's going to be a negative number, which makes sense because there was a reflection with respect to the x-axis because our absolute value is, our absolute function is pointed down. And then I'm just going to pull up my calculator. What is that? I guess that could be like, I don't know, reduced down to 1/4 or something. I don't know. I'm bad at math. 100 divided by 125. So 0.8. Or if you wanted it as a fraction, you could push math, frac, and it'll give you a fraction, 4/5. I'm just going to do 0.8 for now. So 0.8 equals a. So we use 0, 0. Yay. Which 2 points of the figure of the 2-tower design could you use? Do I have to solve this eventually? Oh, yes, okay. Just making sure that I'm not doing all this work for nothing. Which 2 points for the 2-tower design could you use to determine H and K? So here, our vertex, so we're looking at this part right here as being our parabola. So we've got our vertex right there. So our vertex moved from 0, 0 this way, how many units? And then up, how many units? So again, we're going to use this point right there. And I guess I'll switch colors. We'll do this one in green. So our H, or our K, is, let's see, what? How many units up? So that's going to be 20. And our H is 125. And then this time, in order to solve for A, we're probably going to need to use this point. Again, you could probably use any point that you want. It doesn't really matter. I would pick this point because it's got that 0 in it. Every time you have a 0, math just gets way easier because anything times 0 is 0. So we're probably going to end up using 0.70 for our point. So 0.70 and that number, or that point. And so then to solve, they kind of did all the work for me. So they started with here, with their given equation. We substituted in our H and our K values. Oh, no, we didn't. Yes, we did. So we substituted our H and our K values. So our H and our K values. And then we're using 0.70. So anywhere we saw an X, we put a 0, 70, or C2 of X, we put a 70. And then after that, we just kind of did some algebra. So we squared that, got that number. Then we divided both sides by that number. And our A is equal to that. Yes, that's a really weird gross number, but it's math. Especially when you get into the real world, you never have nice numbers. So get used to it. Why is the parameter A negative in the absolute value model but not the quadratic? So that has to do with, in our absolute value, you can see our absolute value is facing down. And whereas here our quadratic is facing up technically. So if we were to extend this, it would go up like this. So you don't need that reflection across the x-axis, which we talked about a little bit, but they wanted to make sure I mentioned it again. So the model for the cable in the 1-tower design is that. The model for the cable in 2-tower design is that. And so then we could find the average rates of change, and we can talk about that. But that's just plugging and chugging. So we're going to move on. Oh, hey, that's the end of this lesson and video. So at this point, you should try the check on learning. And if you need help with that, there's a video for you. Good luck, and I'll see you in class.